So now we're coming to the best part. So this year, our Osterberg Memorial Lecturer is John Wolosick, and to introduce him, because this lecture is sponsored by Food Grow Load Test, we have Dr. Paul Bullock. So thanks everybody for being here.
Welcome to the Osterberg Memorial Lecture. The lecture is sponsored by the Foundation Trust from DFI. The mission statement is printed here, but basically what it is to get new leaders into deep foundations. A lot of people don't know what we do or why we do it. They don't realize how we underpin most of the big cities in the world. So the trust goals are listed here, but basically it's about attracting high school and college students by giving them some financial assistance, by promoting awareness that we exist, and by promoting educational programs to them. So, geotechnical engineering students are the backbone of the deep foundation industry, and they wind up not only being engineers for engineering firms, but also working at a lot of different contractors, because contractors need them too. In fact, our speaker today is essentially a contractor, right? So, since 2006, and this is a big number, the trust has given out almost $2 million to over 500 students. So it's a very worthwhile cause. This year's lecture is the 15th in the series. The first occurred in 2009, was sponsored by Load Test. Load Test is a company that was started by George Osterberg. He was one of 4 founders. 2 of the other founders, Dave Krapps and John Schmertman, have given this lecture. There's a number of well-known lecturers. Harry Poulos, Paul Main did last year's lecture. The Osterberg was a true pioneer. Many of you, if you're in just general geotech, probably know him from sampling and the work he did at Northwestern University. Literally established the program in geotechnical engineering at Northwestern University. But more importantly, revolutionized the drilled shaft industry. The ability to build, test, and confirm the design capacity for 12-foot diameter shafts is just incredible. I mean, we could never have pulled that off with top-down loading. So it was a big deal. This year's lecture, and try not to steal much more of his time because he told me he's going to be here through the break anyway, is John Wolosick. John is with Keller North America. He's a life member in ASCE. Of course, he's a PE, and he does have 45 years of experience. He was a past president of DFI. And he also was awarded the GI CAP Foundation Engineering Award from ASCE. The title has something to do with Davisson criteria and micropiles. And I'm going to let him explain the rest of that. So, John, welcome.
Thank you, Paul. Let me figure this out here real quick. Oh, does it keep going? Yeah, no, I think I'm okay here. I think I'm good. Okay. Okay? Yeah, got it, Matt. Okay. All right. I was telling Teresa ahead of time, I'm usually a wing it guy, but I think in this particular case I probably over-prepared. But I'm honored to give this talk. As Paul mentioned, a lot of great people have given the talk in the past, and a lot of them are friends of mine. Dr. Eric Lohr from the University of Missouri, Paul Main, that you mentioned, from Georgia Tech, and Jean-Louis Briot from Texas A&M. So really pleased to be here. My comments about George Osterberg are that he was a game changer in the deep foundations industry, professor of civil and geotechnical engineering at Northwestern in Evanston, Illinois. He was a fantastic teacher, mentor and inventor. And Paul mentioned he invented the Osterberg cell, which was a total game changer in the deep foundations industry, particularly for drilled shaft foundations. He patented, and that find also started the company Load Test. This is a great photo taken in 2007. In the back row are three of his former colleagues at Northwestern, Dr. Chuck Dowding, Dr. Ray Kryzik, and Dr. Rich Finno. And a lot of you will recognize sitting next to Osterberg in front is Dr. Ralph Peck. So this was at GEO Denver in 2007. And I'm really happy to be here, as I said. So the title of my presentation is, and it's sort of a spill the beans presentation, just like Dr. Hartman did this morning. It's something that I've been doing for 30 years, but I've sort of kept it close to the vest. We considered it a bit of a secret within our company that works so well, but we didn't ever share it. And it is the proposed modified Davisson criteria to evaluate Micropile safe service and ultimate loads. And I'd like to credit also my colleague, Bob Scott, who works in the Keller Nashville office. Always hire people that are smarter than you. And Bob is one of the best foundation engineers you're ever gonna find. And we are gonna write a paper about this. I have the paper about half done. I was hoping to have it done by the time this came around, but life got in the way, pretty busy, and so it's going to be submitted to the DFI Journal, and we will get it published. There's some things that I'm not going to cover in depth, which include hollow bar micropiles, and if we get time, we'll put that in the paper. So the Davisson criteria, what is this? Well, Tom Davisson was a professor at the University of Illinois. He was at Illinois for 50 years total. And he passed away in 2016 at the age of 84. You'll see right here his 50-year medal award being at the university for 50 years. He got his PhD in 1960. His PhD advisor was Ralph Peck. He was an eminent geotechnical engineer. He was a sort of a larger-than-life guy. He was a keen pilot. He had his own twin-engine Beechcraft that he flew. He had a huge consulting business, and he flew some of the other faculty around as well, in some dicey weather in the Gulf Coast region, et cetera. That's a picture of him by his plane. This is not his plane, but one very similar, the twin-engine Beechcraft. He was a piling specialist. He particularly specialized in driven piles, driven H-piles, driven pipe piles, but he also shared some knowledge later on in his career that many people haven't read about drilled piling types. So I knew Tom Davisson. He was my instructor for Civil Engineering 384 when I was at Illinois, applied soil mechanics and foundation engineering. And then when I entered graduate school, he had a very vibrant consulting business, and I worked for him when I was in grad school. So Davisson was paying $9 an hour in 1979, and the minimum wage was $2.25. So you could make good money working for Davisson, and a lot of us knew it. My roommate, Lee Abramson, and Dr. Marco Boscardine, that many of you may know, also worked with me for Davisson, as well as Gabriel Fernandez. So the Davisson criteria was originally established for driven piles, and we're going to be talking about micropiles today, right? So I want to just put this definition up. I'm not going to read it verbatim, because there may be some people in the room that aren't micropile aficionados, okay? So what the heck is a micropile, right? So it's a small diameter drilled foundation element that consists of steel pipes and steel bars, typically in the 3 to 10 inch range, although we're doing bigger ones these days, 16, 18 inch in some cases. The pile is drilled in place typically using rotary drilling techniques where we flush the cuttings out with either water or compressed air or a mixture of both. And then there's a rebar that goes down the center. Oftentimes it's a threaded bar called an all-thread bar, and we grout the hole from the bottom up using Tremie techniques. So that's a bit of a review for people that know about micropiles, but if you're not a micropile person, I'm just trying to set the stage here a little bit. So this is a well-known diagram. It's a 5-step installation procedure for micropiles. One of the interesting things about micropiles in the type that I'm talking about here today is that we use the steel pipe that will become part of the pile as the drill tool. It has a cutting shoe or drill bit on the bottom, and so this is a cross-sectional view of the steps where you've got some compressible soils up here that would settle too much for whatever foundation we're going to do, and then at depth we're looking at something that is more substantial. So in this case, there are 2 sets of tools going down the hole. It's called duplex drilling, 2 sets of tools. There's an outer pipe and an inner drill rod with a bit on it as well. So we flush in this system, and the flush comes out bringing the drill cuttings. We drill through the unsuitable materials down into the denser materials. When we reach that bottom, we put a Tremie pipe all the way to the bottom, and we pump it from the bottom up full of cement grout, high-strength cement grout. And then we also lower, typically, a steel reinforcing bar, an all-thread bar, and then we reverse and start bringing that pipe out. Oftentimes this lower zone, particularly if it's sandy, will be pressure grouted. It can either be pressure grouted through the head of the drill rig, or we can come back and do what's called post-grouting if we put a post-grout tube in. And then typically when we get up to this softer zone, we stop. In some cases, for economics, they might remove the casing. I'm not a big fan of doing that, but so that's a typical installation process for a micropile. So during this talk, I'm going to be using some terminology that I first established when I wrote a paper with Seth Perlman back in 1992. And they're basically, it's a classification where we're looking at soil piles and rock piles, S and R. And so the type 1 piles, both soil and rock, the S1 I just described to you in the previous slide, but it's basically an upper casing that's filled with grout and a lower pressure grouted bond zone that has a centralized reinforcing bar in it, and then some development length up into the casing, and that's a very common type of installation for micropiles. The S2 pile is almost never used. I've only used it a few times in my career, but we were using it more in the early 90s, and it's a pile where we're looking at limiting deflection in soils, and so we get more area of steel in this lower bond zone if we put pipe all the way down. But you have to pressure grout, and then you have to actually drill this pipe back through the pressure grout, which is difficult to do, and so most contractors don't do that. So this is a bit of a unicorn. The R1 pile, R for rock, is where you drill down with the outer casing with the cutting shoe, but when you hit the rock, you typically will refuse, so it stops at that point. So we go inside that pipe then with another drill tool, and we hammer out a rock socket, okay, as shown here. When we do that, we then put the Tremie tube down, fill that up, and then we drop this steel bar in place. The R2 pile is fairly common, and what we do in that case is we go down with 2 sets of tools, and we drill out a bigger rock socket, and then we put this steel pipe all the way to the bottom, fill it with grout on the inside, then typically we'll pick this up off the bottom and then rotate it some and bring it back down again and make sure we get grout on the outside of the pipe as well. So S1, S2, R1, R2, keep that in mind. So my talk is about micropile acceptance criteria from load testing. And many of you are probably familiar with the FHWA Micropile manual, the reference manual. This is the latest version. It's being rewritten right now by GEI consultants, and there will be some updates coming up very soon. But under this particular publication, which has been around since 2005, if you look at what they talk about here for acceptance, they say, well, you can use this method where you're looking at the slope of a line, and when you hit that slope, you know, that should be your failure criterion. And at the bottom, you can see here that they talk about the Davisson criteria, but they say it hasn't been evaluated. And so I'm the type of guy, when somebody says it hasn't been evaluated, I evaluate it. And that's what led to the talk that I'm giving here today. So this is a manual that's used for public works, right? For federally sponsored FHWA type US DOT work. In the private sector, we use the International Building Code. So this is something that's monitored, developed by the structural engineers throughout the US. And when they talk about load test evaluation, they give you these choices here, but you can see on number 1 is the Davisson criteria. And so we've got the federal government saying it hasn't been evaluated, and then we've got the structural engineers and the building officials saying this is the number 1 method that you should use. So a little bit of a disconnect there, but once again, leads along in my story. So what is a load test on a deep foundation, typically if you're not using, say, an Osterberg cell for a drilled shaft? So I just wanted to show you a compression load test is a complicated thing. You have to use reaction piles. There are 4 reaction piles here, and we have this is from a project in Honolulu, Hawaii we did in 2015. And those are tie-down anchors, and then we have a cross beam here and reactions, and then we put a hydraulic jack in, and we push in compression, and we measure the response of the pile under load. And so this is to try to prove the capacity of the pile. So this is a compression test. In micropiles, we often do, because it's less expensive, a tension test. So it's been proven very well that it's a slightly conservative result using the tension test, and it costs about half of a compression test. And so we often use tension tests to evaluate micropiles. This is also one in Hawaii. But much simpler test. There are no reaction anchors. You can just set your reactions on the ground, and you pull on the pile and measure the response. So I hate when people put a slide up and read it, okay? But when somebody writes something that you're talking about and it's really important, these are Davisson's words from his original 1972 paper, and I'm going to read them to you because it's critical for the discussion here today. One of the things that I like and I laugh about is when references from the 50s, 60s, and 70s have words like, "it has been found that." And so that comes up twice in here, and these days I think they make you prove it more than saying it, but when he said it, he meant it, and these are his words, so please listen. It has been found that an offset criterion similar to that used for some metals can be specified for determining ultimate load. Now, I don't know what that means. Some metals I think he's talking about material science, perhaps, which I know he was very keen into steel, but that's his statement. The criterion has been developed for the point-bearing pile by considering the deformation required to cause yielding of the soil at the pile tip. This deformation is known as soil quake and designated Q-tip. For piles of normal dimensions, approximately 1 foot wide, Q-tip is approximately 0.1 inch for most soils. It has been found that when the pile settlement is 0.15 inch plus Q-tip below the elastic index line, the ultimate load can be presumed to have been reached. This settlement criterion can also be applied to the friction pile. It can be seen from Figure 6, which is my next slide, that because of the flat top yield condition for friction piles, the criterion used for point-bearing piles is reasonably applicable, resulting in the same failure load over a wide range of settlements. So that is the Davisson criteria. So Figure 6 that I show here is also in the 1972 paper, and basically he covers, first of all, his criterion, which is we're taking first the elastic deflection, which is just Hooke's law or elastic theory, delta equals PL over AE, and we're plotting that elastic criterion in a load settlement curve, and then we're adding 0.15 plus the Quake. And he shows in this particular diagram that point bearing is what he has assumed in his initial discussion here, but if you look at friction, point bearing, or point and friction, they all cross at the same line, which is the elastic line plus the 0.15 plus the Q-tip. And so he's saying that in his experience and all the load tests that he's looked at, that it doesn't matter what type of pile you're looking at, they may have a different load response. And you can see here, for example, that the friction pile is much stiffer initially, but it has what he calls a flat top failure loading. And so they all cross at the same point, so he's saying it's good for all types of piles. This is a very simple criterion, and I find that things in life that are simple are beautiful, and I like it. So then in 1986, which was 14 years after he originally published this paper, there was a very nice one-page summary of the Davisson criteria, because in the 72 paper, it was a little bit cryptic, but this has a nice little 7-step procedure of how to apply the Davisson criteria. And so it's basically, once again, load versus displacement. And I hate it when people plot the load going the other way, because you push down and things deflect down. So this is the way I like to plot it. And so here's your load deflection curve. Here's the elastic line, which is down here, the elastic theory, delta equals PL over AE. And then he adds the Quake and the 0.15. So these are small numbers. That's only a 1/4 inch, okay? 0.15 plus a 1/10 for a 1-foot pile. And then it's described further on here that you can use for your Quake the diameter of the pile divided by 120. And that's what you'll find in textbooks on many of these projects. So it just has a 7-step procedure. He has some real good stuff here and here. For example, what happens if the pile doesn't plunge? And he says, well, in that case, just take the maximum load you tested to, divide that, and that's your ultimate, and divide that by 2. And that's actually pretty good advice. So let's examine that Davisson criteria. It's the elastic deflection, and then this 0.15, which is 3.8 millimeters. This is my term, plastic deflection. There may be better terms for it, but it kind of makes sense right after the elastic deflection. Plus this Quake, which is the diameter divided by 120. And so that diameter divided by 120 allows you to apply this to different size piles. These numbers, P over AE, you're familiar with, the load, the length, the area, and the modulus of elasticity. So for micropiles, the calculation of the area and the modulus are complicated. It's not like when Davisson had a steel H-pile or a steel pipe pile, because you've got all these different components, right? You've got grout, you've got steel pipe, you've got steel bar, and you have to figure that out. Well, it turns out you can figure that out. So it's a composite system, and it's different than what he had. The other thing that I want to point out is that for micropiles, if you're only in the 3 to 10 inch diameter range, this D over 120 number is a pretty small number, okay? It's much smaller than many of the numbers you would have on drilled shafts or auger cast piles, for example. So how do we calculate that elastic deflection for micropiles? And one of the things I mentioned earlier is that a lot of times these days we're using tension tests. So I'm going to look at both compression and tension because tension testing is so economical. And when we look at tension, and this last sentence here can be discussed ad infinitum, but we're not going to use the grout in tension because it really does not contribute much to the stiffness. Now, it is confined in the pipe up above, and it is a matter for discussion, but I'm going to look at both elastic deflections in compression and in tension. So in applying the Davisson criteria to micropiles, the first thing we have to do is calculate this elastic line. And so it's very simple to use just a spring constant for those lines. And we look at the individual components. But as you can see here in this type pile, the upper zone, section A, has the cross section that has the pipe in it. The lower zone, BB, has no pipe. And so we have to break those apart in order to calculate the different areas to use in the equations. And for a R2 type pile, where we don't have the bar inside, you know, we would just have no bar and we'd have all pipe and all grout, and so it would be the same in both cases. So the other thing is, if we want to accurately predict the deflection, and this is a little bit of the tricky part, what we have to do is we have to look at the load path, okay? And so the load, if you put a load on this pile, we have development lengths of both the casing and the bar. So when you put a load on a bar in concrete, the ACI code has you calculate development length, and that development length is critical for the accurate evaluation of elastic deflection. So keep that in mind. And what we recommend and we found works really well is when we're running these numbers and getting the stiffness, we use 50% of the prescribed ACI development length. And the reason for that is, if you think about it, the load transfer that occurs in a pile system or in any rebar, when you start transferring the load, there's very little transfer, and it all gets down to 100% transfer based on the ACI development length calculation. So it's a triangle. And so if you want an average of a triangle, you can take a rectangle, or you can take a 1/3, 2/3. We just use half, okay? And we found that that gives a much more accurate representation. So Dr. Hartman this morning said he wasn't going to show any calculations, but I'm going to break down and do calculations here for you. I'm not going to spend a lot of time on it, though. So what about that development length? This is the old ACI code. I'll call it the old days. And these are calculations for development length in tension and in compression out of the code prior to 2019. This was from our Hawaii project that I showed before, but you run the calculations, they vary, the equations vary from, obviously from tension to compression, but for a 2.5-inch grade 150 bar that we used here, you got 12 feet in tension and you got 9 feet in compression, but it's a little complicated, but not bad. Well, I'm old enough that I remember that in the old days, all you did was, you know, use 48 bar diameters and you had it, right? But that is not the way it is anymore. So this was pre-2019. So let's look at this real quick, and this will be in the paper, and you can look at it a lot more, but this is an example case where we're gonna calculate a compression load spring constant for this test case micropile. So this is a 50-foot long micropile with 40 feet of upper length and then a 10-foot bond zone. It's a 7-inch diameter, .408 wall thickness pipe, and it has a 2.5-inch diameter grade 150 bar in it, and these are just all of the calculations for the areas, et cetera. Then the materials we're looking at here. Now, a grade 150 bar yields at 120. That's a common mistake that a lot of people make in geotechnical engineering. That's the 150 is the ultimate. So we're putting in the 120 here. The grout strength is 4,000 pounds per square inch. We're using the modulus of steel. We calculate the modulus of the grout from an ACI equation, and then we do a back calculation of the effective area of the bar because it's a thread bar and it's got different thicknesses depending on where you cut it. So the ACI code now has all of these factors, all right? They're psi factors, and they identify, number one, whether or not what the grade of your bar is, what the spacing of your bar is, what the confinement of the bar is, and there's one other one that is escaping me right now. But it's a little bit more of a complicated equation. So in the end, it's going to get longer, right? Because every code makes things a little bit more expensive. And as I mentioned, then we'll go and we'll use half of that. We'll use a calculation to use half of that to get the right numbers. So what we're going to do now to calculate these spring constants is we're going to use the modular ratio concept, which is well established in structural engineering, for transformed areas to calculate and arrive at the theoretical elastic deflections, in this case for compression, just as Davisson described, but he had a simple Hooke's law, but we're going to do this between the upper unbonded length and the lower bond length, and we're going to come up with spring constants that we're going to call K sub U and K sub B for upper and bond, and it's basically just the deflection divided by the load is L over AE. It's a deflection per unit load. It's a spring constant. So that's for compression. In tension, because we have to test the bar by pulling on it, or excuse me, the pile by pulling on it, we run the bar all the way up, but we've got the same test case here, but now we're going to calculate the tension load constants. We go through the same thing. Once again, a different equation from ACI that I'm listing here, and the psi factors, and we get our values down here, once again, modifying the bond length, or excuse me, the development length. So once again, we're going to use transformed area and calculations, but this time in tension, to arrive at spring constants in tension. So to summarize that, the elastic spring constants for the compression test you can see is 0013 inches per kip, and for my friends who use the SI units, I've put the millimeters per kilonewton here. I apologize for the 3 significant figures, but hey, this is structural engineering, okay? So, you can see the slight variation between the tension and the compression results. So that's our P over AE, okay? It's calculated scientifically. So what about the number for Quake? What about that Quake number, okay? So this is a load test from a project in Puerto Rico. Funny because Dr. Hartman had a Mayaguez, Puerto Rico project this morning on his, and this one was also in Mayaguez, but that's a total coincidence. But Quake is described by Davisson as the residual movement after failure load has been reached. So the reason I like this diagram to show you and talk about Quake is that in Puerto Rico, the building code says you have to go to 250%, okay? Not 200 like we have here. And so this is a case in soft clay in Mayaguez, and you can see it's a fairly lightly loaded pile, but we went up to 100% and then cycled back to 0, and then 100% design load is here, 200% test load initially, and then we went to 250%, and I've plotted here my Davisson line, and we just reached it at that point. And so if you think about it, what Quake is, that plastic deformation, we can measure that in our tests. So if you do a micropile load test, you should always take it back to 0 and see what that resultant number is. At 200%, the permanent set was 0.092. At 250, which is encountering the Davisson failure line, it was 0.154. So instead of that D over 120, we can measure that in every test that we do, okay? So in this particular case, though, what I've done, and I'll talk more about this later, is I've used I interchange the upper and free numbers, and the reason I have to do that is because of our software. I apologize, but because everything I'm going to show you later has free length. But I'm using only half the bond length, free length plus half the bond length, instead of the free length plus the full bond length. But you can do either one, and I'll talk about that more in a moment. But this is our Quake. We've just measured it from this pile load test. This happens to be a 45-foot long pile with just a number 11 grade 95 bar, epoxy coated, 8-inch diameter drill hole. So there is the Quake for this particular project. So I wanted to know more about Quake, and so I dug 16 pile load tests out of our archives, and there's quite a variety here, although that most of them are located in the southeastern United States. But I've got many different, most of them, I think about 10 of them are rock piles, 6 of them are soil piles. They're in various locations: Mississippi, Georgia, North Carolina, Puerto Rico, Alabama, Hawaii, Knoxville, Morristown, Chattanooga, all over the place. And so they're different. Some of them have steel pipes, some of them don't. They all have different sizes and grades of rebar. The loads are all over the place, anywhere from 600 kip test load to very small 100 kip test loads. And so what I did with that data then is I averaged the measured Quake that is in this column over here, since we took all the load tests back to 0. And you can see here for the S1s, the Quake was about 0.21. There's the millimeters for S1 piles. For R2, it's 0.05, and for R1, it's 0.14. Well, those numbers seem to match up pretty well if you look over here for just standard US numbers between a 1/16, an 1/8, and a 1/4 of an inch. They come very close. So keep that in mind. Then the next thing is, at the end here, I have D over 120 calculated, and it's as I mentioned before, it's a very small number for micropiles. So this is how I do it. This is how we do it. We take the Davisson criteria, which is this equation here, and then I say, okay, let's use some presumptive values for the Quake. For the R1 pile, we just had an average of a 1/16 of an inch in the previous table, R2 pile. For the R1 pile, an 1/8 of an inch, and there's the millimeter equivalents. Those are rock bond zones. For the soil piles, it's a 1/4 inch, okay? So what we do is we calculate the spring constants for the upper and lower parts of the pile, sections of the pile, as I showed in the previous slides. We run our compression or tension test to twice the design load. If the pile plunges, the failure load is where the test line crosses the criterion. Now, we're geotechnical contractors, and a pile load test failing is often a $100,000 boo-boo, okay? So we don't get a lot of plunges these days, but as Davisson said in his paper, if you don't plunge, assume twice the design load is your failure load if the micropile, doesn't plunge, as I said. Then you measure the Quake, that residual movement. Compare that to the Quake you use presumptively and adjust as necessary. You've just tested the Quake, use it. But while you're running the test, you can use these numbers to indicate if you're having failure or not. Then you confirm the failure load, divide by 2, and that's your safe working load. So this is the way I've done it for 3 decades. So for the test case that I showed you when we did the calculations, which was this 50-foot R1 pile, if you put the numbers in, the test load is 600 kips, and you add these numbers in, at failure and compression, it's predicting 1.42 inches. And that kind of makes sense if you're a pile guy, okay, for a failure load on a 600 kip pile, 7-inch. For a tension test, it's a little bit more because of the ignoring the concrete, it's 1.65 inches. So there's one other thing we have to look at, and that's the length of the pile. So if we're using elastic theory, right, PL over AE, we have to look at L. So let's look at that. Let's look at the length. We have the upper or free length of the micropile and the lower bond length. So several authors have published, and it's pretty well recognized that oftentimes in micropiles, the load only goes about halfway into the bond zone, all right? And that's well recognized in anchors also. So should we use the free length plus the bond length for the L, or the free length plus half the bond length? So I grabbed a couple of papers. This is Gomez, Cadden, and Bruce, where they had some strain gauges just to illustrate this question. And this is a short 13.5-foot bond length where they had strain gauges. And excuse me, if you line up across the way here, they took it to a very high test load. And really, they've connected the dots here, but what I really believe is that this is more of an asymptotic thing down here. But you can see the load doesn't, much of the load doesn't get to the bottom. This is a short pile. A different reference, Holman and Barkakis, where they have a 9-meter rather than the 4-meter. I should have mentioned, this is just a 4-meter bond zone. So this is a 9-meter bond zone, a longer bond zone. You can see that the load doesn't get to the bottom, right? And so the question is, do we use free length plus the bond length, or free length plus half the bond length? And I'm going to talk about that more here. So let's look at some load tests. I've picked out 6 different tests. 2 are in sand in Alabama and Tennessee, 2 are in clay in Mississippi and Puerto Rico, and 2 are in limestone in Knoxville, Tennessee. And let's just see how this criterion works and what the difference is between free length plus bond length and free length plus half bond length. So this is an S1 pile. It was at a paper mill in Mobile, Alabama. Design load was 150 kips, and we've run the load test. We've measured the Quake, which was 0.324, our rebound here. And then if you look at the bottom here, we've separated out the free length plus bond length in the orange, and then the free length plus half the bond length in the gray. And so I look at those 2 lines, and I plot them and look at the response I get. And in this particular case, it looks to me like the free length plus half the bond length is better. But what we're seeing is that we're in the ballpark, that the response from the load test is initially, and it looks pretty good as far as determining the elastic line as described by Davisson. And then I've taken this measured Quake plus the 0.15, and we've drawn the parallel lines for the free length plus half the bond length plus 0.15 inch plus Quake here, and then this is the free length plus bond length plus the failure criterion. So this was a 75-foot long pile with a 20-foot bond zone. So I think that looks pretty good. We're predicting this elastic response well. This is a sand test in Memphis, Tennessee at the Veterans Administration Hospital expansion. We measured the Quake at the end here of 0.076, and then we've plotted those lines, the free length plus half, the free length plus bond, and then the extensions of them. And then our software calculates these slopes of adding both the free length and the bond length together, but you can see the offsets. Now this particular test, it was sort of a research test. I was trying to fail this pile. I took it up to 300%, and it started to bend over a little, but it never did fail. So, but once again, when you look at the response of this pile, this is the 200%, this is the design load here. We're in the ballpark with either one of these criteria, but once again, I think the free length plus half the bond length looks a little better. So now let's move to clay. This is still an S1 pile, but it's in clay at the Jackson, Mississippi airport. And we had two different design loads in this case. One pile was 70 kips, one was 110. So the blue line here is your more lightly loaded pile. It performed fine. We could not get the 110 kip pile to get to 200% no matter what we did. We post-grouted the pile. The soils just couldn't handle it. And this was a 25-foot bond zone over a very long 85-foot pile. So it failed at 173%. But you'll notice in this case that we're not following that elastic line. And this is a really cool part of analysis if you're a geotechnical engineer and you're thinking about what's going on. Well, why would that be? And you think, well, okay, maybe that upper zone is pretty good, or at least it's sticky, right? And so you're getting a much stiffer response because you're not just blowing through that upper zone, it's actually providing some resistance. And Davisson mentioned the flat top yield in a friction pile. And so even though we're not following that elastic line, it comes back around just as he predicted, and it comes down to the failure at this point. We didn't reach 200%. And so this is a lesson learned where if you have piles that have a response that is above the elastic line, that means you're taking load in the upper or free length and it's giving you resistance. This is another S1 clay pile, post-grouted, 80 feet long in Puerto Rico. And we took this one because of the Puerto Rican code to 250%. But you can see, once again, we're in the ballpark here at the beginning for the elastic line. And then we've circled this around. The Quake is 0.154. And then we've plotted the free length bond length and the free length plus half the bond length, and then shown those offsets as shown here. So I think this is a very reasonable way for the engineer of record to assess the performance of the pile and determine what the safe working loads are on a micropile. So here's another one. Now we're going to move over to rock piles. This is limestone pile, 45-foot pile with a 15-foot bond zone in Knoxville, Tennessee. This is also a very heavily loaded pile. Test load was 1,200 kips on a micropile. But once again, you can see here that we're way above the elastic line. And the other interesting point is that the quake was 0. There was no quake. There's no Q-tip because the pile is just a rubber band. It's got a 15-foot rock socket in solid limestone. Where's it going to go? Okay, it can't quake, right? And so what's also happening, though, in this case is, in Knoxville, in this particular project, this was a tank, and it had some very heavy loads, but the soils were not that bad. You know, it was a pretty decent clay, and so we were getting a lot of load resistance in that upper zone, but there was no way that they could meet their settlement criteria for this heavily loaded tank, and that's why it went to deep foundations. And so that's why we're way up here and not anywhere near the line, but it gives you the elastic lines, but it gives you a reasonable way to look at it and interpret the response of the pile. 0 quake. There's another one in Knoxville. This one's a very short pile, only 32 feet long with a 10-foot bond zone. Once again, we have almost no quake, 0.05 inches. But you can see here we're shooting pretty good as far as predicting with our elastic line the way the pile is going to respond. And it's just a big rubber band, right? Where's it going to go with this rock socket? You push on it, it deflects. You take the load off, the deflection comes right back off again. And so once again, I think a really good and a very high design and test load, 450 and 900 kip test load. So it just, in my mind, shows you that the way we're looking at it works. The last comment I have is about creep. So in soil piles, of course, you worry about creep, and Davisson talks a lot about creep in his publications. And so I grew up in the anchor business. You know, we have the creep test from the PTI manual. This is an excerpt from that PTI manual that tells you basically you put the load on. In tiebacks, it's usually 133%, but we're testing piles to 200% because we don't test every one of them too, right? And so I like the PTI manual criteria, but we do it at 200%, not at 133%. So it allows you 1 millimeter of movement over the first 10 minutes. If you exceed that 1 millimeter, you're allowed 1 more millimeter for the next 50 minutes, up to an hour. Above 2 millimeters creep in an hour, it's a failure. So this is a pretty stringent criteria. We plot it up this way in our software that we use in our load testing. So once again, creep's important. You need to check it, particularly in soil and in clay piles, particularly, and this is what I recommend for that. So I think it should be left to the judgment of the geotechnical engineer to evaluate the load test data and to see if it matches his design. So it's up to she or he to evaluate, and I show both on mine, okay, both the free length plus bond length, 100% bond length, and free length plus 50%. And the Davisson criteria seems to do a pretty good job to me, and it has, it doesn't work as well for auger cast piles and for drilled shafts. But in 1993, Davisson had a paper at the Case Histories Conference in Missouri, and it was called Negative Skin Friction on on piles and Other Design Considerations, okay? So those other design considerations that he talked about in the middle of that paper, and this was referenced by Tim Siegel and Morgan Neesmith in their paper about auger cast piles. He says for drilled piles, the Quake number should be 2 to 6 times more than my original criteria said. And so if you look at Morgan and Tim's paper, and you use the evaluation they want, if you use 4.5 times the Quake, you get exactly what you need for auger cast piles. So I've always believed that the Davisson criteria was applicable. And so we think this is a reasonable and useful tool for people to use to evaluate load testing results in micropiles. Maybe some of you do something similar. You know, we got a lot of smart people in this room that have been looking at micropiles for a long time. My question is, maybe Tom Davisson had it right all these years after all. So as I mentioned, we're going to write a paper about this and submit it to DFI, and I really appreciate the opportunity to come. Thank you very much.
Can have one question if anybody has a question. Waiting for the paper. All right, Paul, you want to join me? Just give him his plaque.